is Melanie Lewis, and the project titled Predicting Student Retention Using Enrollment Data will be presented by myself, Yutian, Timothy, and Koby. This presentation will begin with the objectives of this work, followed by a literature review, a description of the data, our proposed work, the results and conclusions, ending with a demo of the application that has been developed. The University of Oklahoma has seen retention rates rise over the past several years. Most recently, the goal of 90% freshman retention was achieved, leading to a current new goal of 92%. At OU, a majority of the work to this point has focused on improving retention through better admissions decisions and early intervention programs. In order to further improve our retention rates, we need to identify other pivotal moments where it is possible to influence decisions that may improve student experiences and outcomes. The objectives of this project are as follows. First, we want to identify common course-taking patterns for first-time, full-time freshmen. Next, we will predict student retention based on the identified course clusters and pre-existing risk factors. And finally, we want to develop tools that can be used by academic advisors to better aid in enrollment decisions, including visualization and a graphic user interface. Now we move on to a summary of some background research related to retention, and specifically work that has been done using data mining to improve academic advising. Traditional research on freshman retention has looked at several psychosocial risk factors. First, there is financial concerns, which represents the extent to which a student is worried about being able to afford college. Academic engagement represents the amount of active energy that a student demonstrated towards mastering and participating in their prior educational experience. Institutional commitment refers to the degree to which a student values pursuing their education at a specific university. And grit refers to the passion to pursue long-term goals and motivation to persevere and accomplish those goals. Financial concern and academic engagement have been shown to explain retention outcomes above and beyond many traditional predictors. There are mixed results regarding the predictive power of institutional commitment and grit, though recent research suggests that grit might influence retention outcomes through its effect on academic engagement. Past academic achievement is commonly used to predict college success. There is strong evidence supporting the validity of standardized test scores and high school grades for predicting freshman college success. While past success predicts future achievement, recent research has shown that this relationship is moderated by specific class decisions. This leads to the implication that advising needs to consider past achievement as well as data-driven approximations of course difficulty when advising students. There are many examples of applications using data mining techniques to create computer-based advising systems. A review of these systems shows that a majority base their recommendations primarily matching remaining degree requirements to available courses. On the other hand, most academic advisors are trained to take a developmental approach, basing recommendations on the student's academic goals, strengths, and weaknesses. A more recent implementation accounts for past academic achievement by matching a student's record to others with similar records, in order to recommend courses based on how those similar students have achieved. The limitation in this application is that it cannot serve students who don't have existing academic records at college. Data shows that a majority of students who drop out of college do so as freshmen, so the most vulnerable group is also the most underserved in these advising applications. The current application is developed to serve college freshmen by entering the recommended courses, past academic achievement, preferred major, and responding to survey items used to estimate psychosocial attributes. This application predicts the student's probability of retention. As such, courses could be modified in order to maximize the probability of success. Our datasets include 2 cohorts of students with data collected during admissions as well as responses to the new student survey, a questionnaire distributed to all incoming freshmen. The admissions data includes up to 7 courses per student, their high school GPA, standardized test score, AP hours, intended academic major, and retention status. The survey data includes a variety of items, and these 149 variables were reduced to 12 for our project. 8 of these 12 items related to past math achievement. The remaining 4 items were composite measures of the psychosocial risk factors.
In this project, we had 2 sets of data mining tasks. The first one is about the clustering the combinations of courses decision to identify which set of classes are the most common amongst college freshmen. The second set is the classification on the clustered data to predict student future retention behaviors. More specifically, we had 3 algorithms for the clustering part. The first is the K-modes, and then the word hierarchical clustering, and finally is the DB scan. For the classification, we did random forest.
Okay, so let's talk about K-modes, the K-modes algorithm. So the K-modes algorithm is a variation on K-means, which lets us process categorical or mixed numerical categorical data. And a fuzzy K-modes algorithm was developed by 1999 by Huang et al. Okay, this is important because you might not always have numerical data, and you might need to cluster it. So it uses a simple matching to similarity, and I show an example there from my Python code, which I implemented K-modes from scratch in for this project. Okay, so it's a simple um, matching to similarity. Okay, so we cluster by modes instead of means for each data point. And it is also a frequency-based method which updates the modes in the clustering process in order to minimize the clustering cost function. So we minimize that function, and that's how we converge on a local minimum of the converged centroids. Okay, um, and the efficiency does scale well with large data sets, which is good news. Okay. Also, I didn't introduce myself. I'm Tim Burt. I did a number of things, but I mainly wrote the K-modes algorithm that we used in this project. Here are some of the plots from the Python code. As you can see, first let's look at the knee plot, which is the cost plot. We see that the knee is right around where k equals 10 or 11, and so we chose k equals 11, um, specifically because of that. We talked about that in class. As you can see from the VRC plot, this is a normalized definition, but the trend is the same, where we see a dip and a spike, and the spike is right around k equals 10 or 11, which is good.
Hi, my name is Yutian Tang. In this project, I was working for the hierarchical clustering, and these are the R packages that I was using. For the very beginning, I had to change my data format from the original one, which had 7 courses as the attributes, to the new one with 630 binary attributes. I assigned 1 to the classes that the individual took the class, and 0 for the classes that the individual did not take. After that, I used Jacob's similarity coefficient to get the proximity matrix for binary data. And then I got this dendrogram. Each leaf of the dendrogram represents one of the n observations. If we move up the tree, leaves begin to fuse into branches according to the observations that are similar to each other. If we move higher up, branches are fewer either with leaves or other branches. The early fusion occurs the more similar the groups of observation are to each other. Observation that fuse later can be quite different. In other words, the height of the fusion is measured on the vertical axis, indicating how different the two observations are. The observations that fuse at the very bottom of the tree are quite similar to each other, while quite different when they close to the top of the tree. After that, I use average select with average method to get the number of clusterings. And from this plot, it shows that the maximum point is when k is equal to 9. So I cut off my original dendrogram to the 9 clustered new one. And here, I show the original tree and the cutted 9 clustered tree side by side. You guys can see it very more clearly. And finally, I use the R packages to get the validation criterions, which has average select, down index, and CH index. And from this table, you can see that the hierarchical clustering is working quite well.
Alright, my name is Koby, and I worked on the DB scan portion of this project. A lot of these packages are the same ones that the other two groups had used. The main difference is I used FPC and DBScan. They both run the DBScan algorithm. However, the DBScan runs much quicker, so that was the one that I really actually was using. I also used the Facto Extra, or the proxy, I'm sorry. The proxy gave me a pretty cool visualization. I will put a caveat that the DBScan works well for very weird shaped clusters. Okay. So in what we did here, we were just trying to reduce our data with the clusters. So since it was such a condensed data set, we only found one cluster with this method. The min points that I used, which is one of the inputs that you have to have, the two inputs are min points and epsilon. I used 20 and 100, and out of the 7,200 points, we found 6,200 points that were in the one cluster that I found, and there was 1,000 outliers. And it actually would have been pretty useful if this was the only data we were using, because it would have gotten rid of 1,000 points that we didn't need because they were outliers. But since we were only using this method on a portion of our data to reduce the data, or the variables that we were using, it really wasn't useful at all. And you can see it here on this plot. You can look at the cluster here. This is a distance. These are all points of distance, so you can tell that they're all pretty much right there together. And as they kind of span out, they all become outliers because they're not within the parameters that I passed in. Like I said, this isn't very useful for this data, and because it was such a globular set. And like I mentioned before, that filtering out the outliers would have been useful if it was the only thing we were using. The three parameters that were used were the Dunn index, the VRC, and the silhouette width. And they were all the minimum points here because there was only one cluster, so of 0, 0, and -1.
Okay, here are the results from the comparison between the different algorithms. So here we have the K-modes clustering algorithm and the hierarchical clustering algorithm. The K-modes was implemented from scratch in Python, and the hierarchical was using built-in functions in R. As we see, all three of these indexes should indicate, as the value gets higher, they indicate having better clustering. And we see that hierarchical is suggested to have the better clustering from all these indices, but it's not that straightforward, because for K-modes we used categorical data. We used the classes directly, each of the 7 classes. But for hierarchical, we had to convert it to a binary structure, which is numerical. So comparing them just with a simple number is not sufficient, and won't tell us the whole story. So to see which one is actually better, what we're going to do is create the random forest with both and compare to see which random forest is going to give us the better results.
Using the random forest package, 500 classification trees were constructed and variable importance was requested. Because classification attempts to minimize the overall error, the imbalance in retention outcomes would cause the algorithm to minimize the prediction error for the larger class. Since our interest is in improving retention, we are more concerned with accurately predicting the smaller class. In order to deal with this imbalance, a downsampling approach was used. This approach balances the classes by sampling fewer observations from the larger group. This is an example of a classification tree, though not necessarily one that was produced by the algorithm. Using random forests, the prediction of each tree serves as a vote, and the fraction of trees predicting that a student is retained over the total number of trees represents the probability of retention. Here you can see that the error rates and AUC values produced using K-modes clusters are relatively similar to those produced using hierarchical clusters. Because the hierarchical clustering requires a much more complex data structure, the application that is developed uses the K-modes clusters. This graph represents the relative importance of each predictor across 2 different measures. As you can see, the random forest algorithm suggests that the cluster IDs are important predictors of retention.
Alright, here is the conclusion part. The good side is the variable importance that suggests that the cost cluster variable contributed substantially accuracy to classification of retention outcome. And then we also find that the random forest support the importance of traditional predictors of retention. However, on the other hand, we have some limitations of this project. The imbalance in retention outcomes could not be completely corrected by the random forest algorithm using the recommended approach. So the error rate was kind of higher than we expected. For the future direction, we would suggest that alternative classification algorithm that deal with the class imbalance should be pursued for. And also, we would suggest a more clustering algorithm for categorical data should be tried.
Okay, so earlier in your presentation, you probably have learned what we're doing here. We're predicting student retention. My name is Koby Pascual. I'm going to go briefly through the code here. We use Python in PyCharm. This is Python 2.7. It's what I prefer. We do all of our coding here except for what we found this package, this rpy2, which is pretty nice. We actually can run our scripts through that rpy2, so we can send our data from Python into the R script, and it'll actually return the prediction, so we can use it to predict retention. So here's our little app. It's very simple, not too much to it, just a little opening message here. There's two options. You can add a student or you can look at the tutorial. So here's just a brief description of how it works. Obviously, you click the one button that's on the screen. Now you have to fill out everything here according to this structure. So these need to be numeric values. This has to be structured like this. If there isn't a course, you have to put a period there. Sometimes 3 or 4 of them aren't there, so you have to have periods. If you don't do it, it's going to yell at you, obviously. So you keep going. You have to fill out these 4 surveys, which are all concerning different things. This is financial concerns, so you have to have this. You can only fill out 1 check per question, or else it's going to get mad. You also have to fill out 1 check per question. You can't do less. You can't ignore 1. The reason is these 4 surveys are actually 4 different data points the data points are numeric values that get calculated from the results of the survey. So once you finish the 4 surveys and the fields, and as long as you did it correctly, you can click submit, which is what you saw here. And then simply look, it goes through and classifies success based on our algorithms. It seems like this student is bound for success at OU. Retention is highly probable. Good news. Unfortunately, not everyone gets to experience that, so unfortunately the results. So the reason we do this is so maybe an advisor can say, hey, you know, with these attributes that the student has, maybe this isn't the best path for them to start out in. You know, not to discourage them, but maybe they can enroll in less courses or something like that. I'm not an advisor, but okay, so we'll run through actually adding a student. So I have some points here of a student that I know that actually passed this. Actually, I have that to where it doesn't matter if it's a lowercase or not, but whatever. Alright, we're going to continue. So this is easy. Agree. Alright, institutional commitment. They love OU. Alright, now we're going to submit. Uh-oh, I made a mistake. Oh, look, geometry I didn't put in. Thank goodness for programming. Alright, success. We're going to succeed. Alright, now I'm going to do one more really quick so I can show a fail. Luckily, I'm able to show a fail here pretty quickly because I actually kind of included a cheat code, so I didn't have to go and actually look for someone that failed for this tutorial, or for this video. Fail. Probably should have made just a quick jump to the end option, but alright, we're not going to graduate, unfortunately. But that's it. Pretty simple application. We want to add some more things I have in the works where we can have a log so you can actually look back at all the other people that you input, as well as adding all the plots from our clusters. And I actually already have this fix in, but I don't know if it's going to be ready by the due date, where you can actually choose the different cluster method that we're going to use. Thanks.